because when Young performed this double slit experiment, people, physicists, are highly convinced. Oh, okay, so light is a wave. Now Newton, the famous Newton, he thought light were particles. Right? So this controversy whether light is a particle or wave has been going on for centuries. Okay, it's not new. All right. So water waves. Now how about something that's really obviously particles? Like, let's say machine gun bullets. So your source here now is a machine gun. So you have your machine gun and you're firing it away. And the bullets are flying out of the machine gun. Now most of them get absorbed by the barrier here, but some of them, of these bullets, machine gun bullets, go through the slits. Right? Now on the observing screen on here, on the right hand side, you'll get two distributions of the number of bullets as a function of distance. Now you get a peak distribution just behind this slit. So that distribution would be the bullets that came through the upper slit. Okay? And this distribution of number of bullets as a function of position, this peak, they'd be the bullets that came through this slit. Right? So when you're talking about particles, you expect to have like two peaks in the distribution as a function of position. And that's characteristic of particles, right? That's what you'd expect. That's pretty well common sense. Now, I've done it for waterways. You get an interference pattern. And how about now for wavicles? Let's say we shoot through individual. Let's say the light. Let's say we're using light. And the light source here is so weak that we're just getting one photon going through the double slit barrier here. One photon per second. So the intensity of the light, the source of the light, is so weak that only one photon is shooting out per second. What happens then? So we look on the photon as a kind of wavicle. It has wave properties and particle properties. Einstein showed that light had particle properties with his famous, what's it called? Photoelectric effect, right? And linked with Planck's ideas. So the question now is, so if you send a single photon through this system, this double slit, or a single electron, just one electron at a time, what happens? So now, if you could argue, if the wavicle, let's be concrete, let's say the photon or the electron, if they are particles, then you would expect the particle to go, like the bullet, like the machine gun bullet, to go through either one slit or the other. Right? That's just what common sense, our human scale physics would expect, classical physics, Newtonian physics, that the bullet goes through one slit or the other. It cannot go through both slits. Right? That would be absolutely counter common sense. You can't have a bullet, the same bullet, being in two different places at once. A bullet, one bullet, cannot go through this slit and this slit at the same time. Nuts. That would if you really started saying that out in the street, people would they'd cut you off to the funny farm, to the lunatic asylum, right? They're just so anti-common sense. All right. Well, what about at micro particle level? At the quantum mechanical level. What about then? What happens then? So does an electron or a photon, does it behave like a machine gun bullet? So will the distribution at the observer screen here, will it be like this? Will you get like sort of two peaks in the distribution, suggesting that the particle goes through either one slit or the other? So you get like a machine gun bullet distribution of the number of particles detected on the screen as a function of distance, right? So you get this kind of pattern, or will you get like a wave type interference pattern? Will you get something like this? Right? And remember, we're just sending one photon or one electron through the double slit apparatus at a time. So what actually happens? That's the interesting question, fascinating question, right? Well, what happens is, let's say we're talking, well, it doesn't matter, electron or a photon. Let's make this screen here highly sensitive to the arrival, the local arrival of an electron or a photon. And so when that happens, you get a highly local, very narrow region, flash of light. Like so, well, let's say we're talking about electron. Keep it concrete, even more concrete. So let's say now we have an electron source. The electron somehow gets from here to the screen, and we're not observing it, so no interference, or the electron somehow gets from the source to the screen, and when it hits the screen, you get a little flash, highly localized flash of light. Right? So we know that that particular electron has hit the screen, I don't know, let's say here. You get a little flash of light. Okay? So so for each little flash, put a little cross X where the electron hit the screen. Right? Okay, now do that again. So send through a second electron, and somehow it gets from here to here, and then there'll be a second flash, highly localized, very small region of space along this screen, specially coded. Let's say it's a zinc sulfide screen here, and when the electron hits that screen, it generates a little flash of light which can be observed. Okay, now, so you do this many times, and what will your screen look like? With all your little X's indicating the position where one electron hit the screen over time. So you get lots and lots of X's. So you can build up a distribution, like this axis. This axis is the number of electrons hitting the screen in a given region of delta X. Okay. Now, will that distribution, will it look like the machine gun bullet distribution, or will it look like the water wave or the wave distribution? Will it have like just two peaks like this, or will it have an interference pattern? Have a guess. Have a guess. So we're trying to ask whether this electron is behaving like a particle or a wave. Now, when it hits the screen with its highly localized little flash, that's very much particle behavior, right? Because it's highly localized and it's generating a little, highly local flash of light. So, in terms of position, where it arrives on the screen, highly local. That's characteristic of a particle. So, the wave in the double slit experiment, when it hits the screen, is behaving like a particle. Okay, seems common sense. All right. Now, the interesting thing is, if you perform this experiment umpteen times, so you're sending through zillions of these electrons. They go through. They start from here and end up on the screen as flashes. You do that many times, and then you look at the distribution pattern on the screen, and the answer is this one. You get an interference effect. Right? You'll get a peak in the middle, and then very few electrons arrive here, and then quite a few here, and none here, a lot, none, a lot, none, a lot. You get this interference. So the distribution of the number of electrons arriving, that's along this axis, and this axis is position. With many electrons, you get an interference pattern. Huh? Now think about that, because it's absolutely amazing. What does that imply? Does that mean? Now remember, only one electron is going through this system at a time, 1 per second. Okay, so it's not as though you have several electrons with the de Broglie wavelengths somehow interfering with each other. No, there's only one electron going through the system at a time. Okay, so to get this interference pattern implies that you've got two slits open. Like now, if you close one of the slits, if you block this one, say, then of course this will disappear. You won't get that. You'll get this, you know, with just one peak. That's as you expect. And if you block this one and open that one, well, you'll get something like that, right? That makes sense. But when you have both slits open and one electron's going through, whatever that means, at a time, you get an interference effect. So think about that. So does that mean that this wavicle, this electron, knows that both slits are open? Because how else do you explain you get this interference effect? Because that's what you get empirically. It's been shown. The experiment's been done. You know, this famous experimental result by some Japanese and later Austrians, where individual electrons are shot through, and over time you see all these dots, and you know, first just a few dots, and then hundreds, and then thousands, and then millions, and okay, and you build up bit by bit, particle by particle. You get this interference pattern. So that's experimentally conserved. That's what's happening. So it's looking as though the single electron, as it goes through here, knows about the fact there are two slits open, because how else do you explain the interference effect, right? Now, presumably, and when that electron hits the screen, it makes a highly localized flash of light. So when it hits the screen, it's behaving like a particle. Okay? But interestingly, where does it hit the screen? Well, it's much more probable that it'll hit the screen here, and highly improbable that it'll hit the screen at these 0 points. Right? Very few electrons arrive at these points here in the interference pattern that have very low values, or 0. Okay, so the electron, in that sense, you know, where it hits is obeying a wave-like probability distribution. Right? It's generating this interference pattern. So, but that's wave-like. Right? It's waves that generate interference patterns. So what does that mean? So now, if you were De Broglie, you'd probably say, well, in terms of my De Broglie, I'm pretending to be Louis Prince Louis. That's his given name, De Broglie. With my De Broglie's, my pilot wave theory, what's happening is that the particle, the electron, is like a surfboard on a wave, and the wave is extended in space, spread out in space, and the wave goes through both slits, right? And here, in this region, the two waves interfere with each other, but there's only one particle, one surfboard, right, riding all these interfering waves, and the surfboard, the particle, hits the screen somewhere in one local place. That's all common sense. Okay, and where it hits is